All right, so today is the last class. Just a reminder, the exam's due tomorrow night. And by the way, if you're interested, I'll also post some extra credit. So you guys can check that out if you're interested. You don't have to be, but sometimes people are. All right, so anyhow, let's get right to it because, well, lots of emails coming in the last couple days, so we got to make especially this new stuff clear, or at least as clear as we can do it. So last class was big, so let's sort of set the stage, and then we'll talk about this homework 10 problems that I know some of you have been curious about. So here's sort of what you should take from last class. Last class, we defined what we call the definite integral. Now, let me be very clear because this is part of the confusion, I believe. So there are many equivalent ways to do this. So if you are reading the book, they define the integral in one way. If you read another textbook, they will define it likely very similarly. Some books define it in a little more general setting than others. Here's how we are defining it. This is our definition. Our definition. And this is, our definition is specifically for a continuous function. So now, in general, you can define what we're going to do, but what we're doing is we're making a simplified version. In my opinion, this is the way it should be done in calculus. So here we go. The integral is written by this symbol. And what it is equal to is it is equal to the following limit. It is the limit of some thing delta x with, and then it's times this sum, which is f evaluated at x of 1 plus f evaluated at x of 2. This sum goes all the way up to x of n. Now, we told you what these symbols mean yesterday. Delta x is b minus a divided by n. And x sub k is always equal to a plus k times delta x. So the first thing you have to do is you have to understand that this is indeed a very complex definition. It's extremely complex. It takes a lot of effort on your part to learn this. And I got to be honest, I think the best way to learn this is to not watch videos as much, but it's to actually get your hands dirty. Try to write out what this thing means. Think about the motivation. So the motivation for this definition was f of x sub k is the height of a rectangle, and dx is the widths. So we were taking a bunch of rectangles, in particular n. Maybe n is 4, maybe n is 32, maybe n is 500. And we're going to say every rectangle has the same width, delta x. And then each one of their heights is going to be some point on the curve. Well, we're going to choose simple ones that we can formalize. Now, if you read the book, they're going to tell you you can choose any point on the curve for the height, and that is true. There's nothing wrong with that, but we are picking specific ones. So if you're following along, and I know this was confusing to someone, not someone, but a few of you, I got a fair amount of emails. Is the following. So, and again, so the sum f evaluated at x sub 1 plus f evaluated at x sub 2 plus this guy where x sub k is equal to a plus k times delta x. This is called a right Riemann sum. So for those of you reading the book, you're going to read about the midpoint. You're going to read about a left or a right. You might even read about a general Riemann sum. Those are all valid. My point is, as a learner, and for me, why try to learn 5 things at once? Learn one of them. Understand a right Riemann sum. And then you can go on trying to tackle understanding the problem in general. That is just my advice. That's my philosophy. Why try to learn 4 things instead of just learning one first and then using your knowledge of the one thing to understand the other pieces? So you'll notice if you look at the homework, particularly problems 4, 5, and 6, I said use a Riemann sum. I don't care which one you use one. If you like right, use right. If you like left, use left. If you want to use some crazy unique one that's unique to you, that's fine, but I wouldn't do it that way. Okay, so so here's an important remark. And I said this on Tuesday, it's worth saying again. While area was our motivation for the above definition, remember our goal was to try to understand the area of curved regions. And so one idea we had is chop it up into rectangles. Maybe we do 4 rectangles. Maybe we do 100. Maybe we do 1,000. And what we realize is that there is a pattern that as the number of rectangles increase, something happens, a limit occurs. We tried to illustrate that last class. So since this limit occurs, we say, okay, maybe we can define this mathematical object and maybe it can be of use to us. So while area was the motivation for the above definition, the integral can be used for many more things. Many of you will get to see that next semester or in physics or in some other classes. So you need to understand that area is only an application. All right. So couple things that are important. We have to get this out of the way, and it's going to be frightening I'm well aware of that for many of you, but we have to come to terms with writing sums like this takes up space. Writing a sum like this takes up space. And so what we've done is we've adopted what we call shorthand notation. And we need to touch on that briefly. We're going to try to avoid it when we can, but sometimes look, you have to speak in the language that everybody else speaks. And the language that we use is what's called summation notation. It allows us to write big, long, scary things in short, compact things. So it's convenient to adopt a shorthand called summation notation. Or some people call it sigma notation, because we're going to use the Greek letter sigma. So what we're going to do is, instead of writing all this out, like f of x sub 1 plus f of x sub 2, what we do is we compact it. Oh, excuse me, I wrote that wrong. So we're going to compact it. This left-hand thing, the way you got to read this is just, this reads, so this is first the Greek letter sigma. Why do we use it? Sum, sigma, SS. And the way you read this is, this reads, the sum of, or the sum as k goes from 1 to n. So I know this is new notation for most people. It's overwhelming for us when we first learn it. And so what you need to do is you need to understand that experience is the best medicine. The more you are around it, the more you work with it, the more comfortable you'll become with it. So another thing that's useful to keep in mind is the letter K is called the index of the sum. So it might be worth your while to sort of get some practice with this. And so I did, on your homework, what I did is I gave you some practice in the first 3 problems. And so let's just look at some examples of how this, and they're going to be very similar to your homework problems. And then we're going to sort of move on and get to the problems that everybody's had. So I want to write, say I have this sum, 1 plus 2 plus 3 plus 4, and this thing goes all the way up to, say, 100. So let's say this is 99 plus 100. Well, how could we write this in sigma notation? How can we compact this? Well, one way of doing it is to say we're going to let k be 1, and then we're going to go up to 100, and we're just going to add those k's. We're going to add 1 plus 2 plus 3 plus 4. Does anybody have a question about this? All right, now, let's do another one that's maybe the pattern. Let's do a different pattern and see how we do. What if I have something like 1 plus 4 plus 9 plus 16 plus, let's say, all the way up to, how about 81? How could we write this in shorthand? Well, one thing you could do is you can recognize that each one of these terms is a square. So you might say k goes from, this time, you got to be very careful. You might go k goes from 1 to 9 of k squared. Now I'm squaring each term. Okay, now, so let's do one more that perhaps is clear. How about we had something like this? How about we have 1/2 plus 1/4 plus 1/8 plus 1/16. Let's say all the way up to plus 1/64. What is this guy? Well, one way to shorten this is to say this is 1/2 raised to the power k. K goes from 1 to 6. So you might want to play around with these examples. Make sure you're comfortable with them. Okay, so it's useful to know how to quickly add these up. So some of you email me freaking out about number 4, like, are you supposed to add 40 numbers? And I hope to God you didn't, because that's like, you know, that's a task nobody wants to do. And so what we look for is we look for patterns so that we can take the easy stuff away. And that's really, as I said many times before, one of the goals in mathematics is to recognize patterns. And particularly when you have things you want to compute, it's very nice to have patterns to shorten these things up. And so it's worth pointing out what we showed you last class. I'm going to state it again. And this is an important theorem. And again, some of you may have seen these in an algebra class, maybe not written like this. Here are some special useful sums. So we told you this before. We said, okay, let's just add up the first n integers. So if I want to add 1 plus 2 plus 3 all the way up to some number n, we told you last class that this is just n times n plus 1 over 2. And then if we want to add the squares up to some number n, well, this is 1 plus 2 squared plus 3 squared plus all the way up to n squared. This is always, it's a little more complicated, but it's n times n plus 1 times 2n plus 1 all over 6. And then you could do this for all powers of k. We'll just write one more down because it could be useful in the homework. If I want to do the cubes instead, like 1 plus, let's write this like 8 plus 27. 4 cubed is 81. Excuse me. Excuse me. 4 cubed is not 81, it's 64. So, and if you go all the way out to the nth number cubed, well, this has a little more compact formula. These are all, you can derive all these using some tricks in algebra. If you're interested in it, I'm not going to do it, but if you're interested, go online and check them out. Just Google sums of integers, sum of first n integers, and you'll see all how to derive them. Okay, so let's use this now. These things can come into use, and this is something that you have to know how to do. So let's put these ideas to good use. So particularly, let's look at the homework. Homework problem 4. So homework 10, number 4. So here's the key idea you need to know. Key idea. By definition, this thing is equal to some limit. What is the limit? The limit as n goes to infinity of this Riemann sum. This is the definition. But what this means is, this implies what we know about limits. It implies that if I don't take a limit, but I just add up 5 rectangles, 26 rectangles, that I get an approximation if I just do n rectangles without taking a limit. So in my opinion, a good way to get a feel for this is to do an exercise like number 4. So let's do it. And so hopefully you'll see precisely what I mean by this. All right. So let's check it out. Before we do that, does anybody have a question about this? All right. All right. So, to do this, so let's start with n equals 4. Now, some of you will get good at this and be able to kill the problem right away. You'll recognize the pattern, but let's build to see if we see the pattern. So let's start with n equals 4. So when n equals 4, what is our delta x? Our delta x is 1 minus 0 over 4, which is 1/4. Now, what happens is it's hard for us to get these x sub k's, and so what's a good thing to do is to draw a number line. This is useful for helping visualize this. If I have a number line, remember, I'm only interested between 0 and 1. Why am I only interested there? But look at the bounds of my integral. 0's the lower number, 1's the upper number. And so if I want to break this into 4 pieces, all of equal width, the way I do that is chopping it up like this: 0 to 1/4, 1/4 to 2/4, and then 2/4 to 3/4, etc. So if we want, we typically give these guys names. We call this guy x sub 0. We call this guy x sub 1. We call this guy x sub 2. We call this guy x sub 3. And we call this guy x sub 4. You'll notice that if you use the formula from, don't get too overwhelmed. You could have also used the formula that x sub k is a plus k delta x, which in this problem is just 0 plus k times 1/4. So you can use this formula, or you can just sketch a number line to get your points. Does anybody have a question about this fact? Another important thing to note for this problem is that f of x equals x. So that means when you plug x of k in, it just spits out x of k. That's the function we are attempting to study, f of x equals x, which means when you plug x of k in, it spits out x of k. You plug 10 in, it spits out 10. You plug -6 in, it spits out -6. If you plug 1/4 in, it spits out 1/4. If you plug x of k in, it spits out x of k. All right, so now that we've done all the background work, sort of got our puzzle pieces laid out on the table, we've separated the edges of our puzzle, and then we're going to try to piece together our puzzle. What can we do here? Okay, well, let's just go through it very carefully. We know the integral from 0 to 1 of x dx by definition is that limit. Now, if we only use n equals 4, we get an approximation. That approximation is delta x times f evaluated at x of 1 plus f evaluated at x of 2 plus f evaluated at x of 3 plus f evaluated at x of 4. And so if we plug these numbers in, this is 1/4. And then it's 1/4 plus 2/4 plus 3/4. And instead of writing 1, I'm going to write 4/4 because I'm looking for a pattern. That's what I'm looking for. You might not be. You might just go plug those numbers into a calculator. And that's fine. If you do that, you're going to miss the pattern that helps you when n is large. So does anybody have a question about how I got this piece? Now, remember that sort of weird way we looked at this sum on Tuesday? Instead of adding it up, I'm going to factor things out. I'm going to look for a pattern, and one pattern I recognize is that I can factor a 4 out of everything. So this is 1/4 squared. And then what I'm left with is 1 plus 2 plus 3 plus 4. Now, one more time, I'm going to abuse this pattern. If I go to the previous pages, I want to take advantage of this thing. I want to take advantage of this shortcut. Even though I can do these numbers in my head, that's not the point. I'm trying to gain intuition for what's going to happen when n is not 4. So let me repeat that. I know I can do these numbers. I can add this up in my head if I wanted. 10/16. But that ain't the point. The point is to see a pattern. And so what I'm going to do is I'm going to write this, and I'm going to use the pattern. This is 1/4 squared, and then this is times. What's the n here? The n is 4, so it's n, which is 4. So this is 4 times 5/2. And so I want to concentrate on this pattern. And of course, now we can compute this if we wanted. So you have 5 over 8, right? Because the 1, 4 cancels, so this becomes 5/8. Which, of course, you can go into a calculator and approximate. I lost my pen. Why did my pen go away? And what's 5/8? 5/8 is, what in the heck? It's losing my stuff. 0.625. All right, so does anybody have a question about this piece? Where I got a number from or anything like that? Anybody chatting? No.
I have a quick question.
Yes.
Can you do it where you like multiply the 4 by 5 and then divide it by 2 and then
Yeah.
it's the same thing?
What do you mean when you multiply it by 2?
Like you have the 1 over 4 squared times 4 times 5 over 2.
Okay.
Can you do the 1 over 4 squared just times 10?
Sure. Yeah, you can multiply it however you want. Yeah. I'm not. What I'd like to point out to you is what you see right here. This sort of the pattern, because this pattern is going to be true no matter what n is. I mean, when you do it in the next case, the pattern's going to carry over, and that's the whole point, is recognizing the pattern. Once you get to this point, right here, once you get here, then I don't care how you do it. You can plug it into a calculator, you can do it mentally, whatever's easier for you, as long as you do it correctly. But the more important, the deeper picture here is how did you get there? Why did I write it this way? Does that make sense? Maybe?
Yep, I'm good now.
Okay. All right, so there we go. Okay, so now what we want to do is we want to do it for 8. So, and once you do this a couple times, what you start to recognize is okay, I see it. I see something happening. So now what's your delta x? This time it's going to be 1/8. And if you're still unsure how to get those values, those x sub k's, just draw a number line, break it into 8 pieces. Here's 4. Now I have 8 pieces. And if you do this carefully, like you're back in 5th grade, don't think about all the calculus. Right away you'll say, okay, I get it. This is 1/8. This is 2/8. 3/8. 4/8. I know it's a half, but let's write it as 4/8. 5/8. 6/8. 7/8, and then the last guy is 8/8, or 1. And so now, being that we've sort of got the hang of it from the first time, now with n equals 8, we know that this integral is approximately delta x times f evaluated at x sub 1 plus f evaluated at x sub 2. Now, I'm not going to write them all. This is 1/8. And then what's the first guy? Well, this is 1/8 plus 2/8 plus 3/8. And then it goes all the way up to 8/8. And so just like on the previous page, look at the pattern. Pull out an 1/8. Now I'm left with 1 over 8 squared. And then it's just 1 plus 2 plus 3, 4, 5, 6, 7, up to 8. And then now I can remember that formula, and this becomes 8 times 9 over 2. This is a square. And then, of course, once again, the 8s cancel. One of the 8s cancels downstairs. So you're left with 9 divided by 16. Does anybody have a question about this? And of course, if you do the division, you can write this as a decimal. This is 0.5625. So now you should be able to see the pattern. Like I said before we did the first one with n equals 4, if you know the pattern right away, you could kill all these pieces in one fell swoop. So again, look, if you look at this piece, 1 over n squared times n plus 1 over 2. Look at the previous page, 1 over n squared times n plus 1 over 2. So what we can say is for n, for any n, delta x is 1 over n. X sub k is just what? Well, it's k over n. Thus, the integral is approximately delta x, and then it's this sum f of x sub k. Or excuse me, let me go more slowly here. So this goes all the way up to f evaluated at x sub n. And let's be real careful. What is this if we write this out? We'll just do what we did before. Delta x is 1 over n. Inside, you get x sub 1. Well, that's just 1 over n. And then that's plus 2 over n, plus 3 over n, plus all the way out to n over n, just like we did in the 2 previous examples. And then just like we did in the 2 previous, factor out the common guy. The common guy is n, 1 over n, so I get 1 over n squared, and then I'm 1 plus 2 plus 3 all the way up to n. And then this is 1 over n squared times, and then this just times n plus 1 over 2, which of course simplifies to n plus 1 over 2n. So now this is your shortcut. This is how you can easily do it for 40 or 100. Because now whatever you want to do, the number of rectangles you want, you could just plug in here. So for fun, I know I didn't ask you to do this on the homework. Let's make a table. Before I go to the next page, does anybody have a question? All right. So for fun, we'll just do a table real quick. So I'm gonna give a name. So this is n. let's make this column our ends. We already did 4, 8, we're gonna do 40, we'll do 100, then we'll do 5,000, and then we'll do 10,000, just for fun. And then what are we gonna put in this column? Well, let's call it A sub n, but let's just say A sub n, remember that name we gave it the other day, was this, 1 over n. Oh, we know it is. We figured it out. It's that from our previous page. N plus 1 over 2n. Which, of course, we know is approximately this thing. So now you could just go right to a calculator. Again, when n is 4, what did we find? We got 0.625. When n is 8, what did we get? We got 0.5625. Now, you plug 40 into that formula. Let n equal 40. When n is 40, you get 0.5125. You plug it into a calculator with 100, you get 0.505. All I'm doing is plugging these numbers. Now I'm going to take for 5,000, I'm going to take 5,001 and divide it by 1,000. So when I do that, I get 0.5001. And then the last thing I'm going to do is for 10,000, and I'm hoping that you see the pattern. So now it's 50005. And so the graph tells us what we may have already concluded, and that is that the integral from x dx is the limit of this. But we know what that limit is. It's just 1/2. And that's exactly what our experiment with n rectangles has shown us, at least in sort of, I won't say shown us, but it's suggested to us. So that is how you do problem 4 on the homework. So the reason I wrote problem 4 the way I did is I was trying to get you to inspire you to recognize this pattern. And so when you do problem 5 and then do problem 6, which we already did in class, I hope that you'll look for the patterns. And then once you recognize the pattern, you get A, B, and C for free. Does anybody have a question about this? By the way, this should also agree with your intuition in the area idea, because if we draw a picture of the function y equals x, if this is the point 1, and of course this is 1, what's the graph look like? Well, the graph we know goes through this point, 1, 1. And so if I draw this line and I look at the triangle, if I look at this triangle that I'm shading red, from elementary geometry, you know what that triangle's area is. It's 1/2 base times height, or 1/2. So this integral, the good news is the integral is a much more sophisticated way of defining area, but it gives us the results we expect from elementary geometry. Any comments of this? Questions? Anybody? Everybody alive? It's Thursday, my favorite day of the week. Basketball's back tonight. Although that would be very, I don't know. Maybe you guys do care about basketball. I don't know. All right. So here's the thing. Doing problems like this is clearly inefficient. And of course, many of you know there's an even easier way. One of the sort of highlights of human achievement actually is that what we're about to show you is you can turn these look, these calculations were quick now because it's 2020. But if I gave you this homework problem 50 years ago, you'd be screwed. How would you have done part C 50 years ago? It would take you forever. We're fortunate now we have calculators that can do it, but without recognizing that pattern, it would have been damn near impossible. Well, at least in a reasonable amount of time. And this problem is an easy function, so the pattern is easy to recognize. If I just give you some arbitrary function, the pattern is not going to be as easy to recognize. So what we do is we need some more sophisticated ways of doing this. And luckily, the derivative of all things is going to save us. So the way I'd like you to think about this is the following. Is there an even easier way to evaluate this integral? I mean, we had to recognize some ugly pattern and take a limit. But what we're asking, is there an even more beautiful, concise, or simpler pattern that we could take advantage of? And the answer is yes, if we look at it from a different perspective. So what we're going to do is study something called the fundamental theorem of calculus. So to motivate it, we got to get real awesome. Let's create a new function. I'm going to call it A of t, and watch how I'm going to do this. I am going to leave 0 down here, but upstairs I'm not going to put a number. I'm going to put the letter t here. So whatever number you want to plug into A, it becomes the upper bound of my integral. So what is this function, what is it good for? Well, what you'll notice is A of t gives the area of the triangle below. So let's look at it. So let's draw the picture just like we did before. So let's assume that t is some positive number. And of course, then this would be height t, and this is the point t comma t. And so if I draw the line y equals You know, if I draw the line y equals x, that's what this is. Or f of x equals x. So let's think about what we know about calculus so far. What is the area of the triangle? Well, we know it's 1/2 times base times height, which in this particular problem is 1/2 t squared. But it's also equal to the integral from 0 to t of x dx. Which, of course, we also define by definition as a of t. So I just wrote a bunch of things that are equivalent down, but there's something hiding in there that we got to take advantage of. What I want to bring your attention to is this. This thing, which happens to be equal to this thing, and then look about what happens if I take a derivative. Note, a prime of t is just t. Now, you might think on the outside that that means nothing and it's not important, but it's actually very, very, very important. Because what it's suggesting is that if you look at the integral and the 1/2 t squared, it looks as if the integral is somehow related to the derivative of the integrand. Here I get t, but what's the function we're doing inside? It's just x. So the function f of x equals x and the function f of t equals t are the same thing. So, and it might not be completely clear to you, but what this suggests is, let's draw this, make sure we're well aware of it. So stars suggest integrals are related to derivatives. And this was actually the big connection that was made by guys like Newton and Leibniz a couple hundred years ago. They recognized there was a connection. It turns out they are inverses in a sense of each other. So what we can do is we can do the following. And we don't typically do it in Calc 1, but you're more than capable of understanding it if you try. So using properties of the integral, along with the definition of the derivative, we can deduce the following: the fundamental theorem. Of calculus. There are two parts to it. The first part is as follows. That if I have any derivative, if I take a derivative of anything that looks like this, so I'm going to switch my letters around. This is just common to do. So this is going to look very frightening to beginners. But basically what this sentence says is if I integrate, then I differentiate, I get back what I started with. So think along the lines of if you take the number 5 and you square it, you get 25. But then if you immediately take the square root, you get back to 5. And then the second piece is the one that you will use more often in calculus 1 and 2. But it says that if you want to compute this thing, f of x dx, then it comes down to simple arithmetic, provided g is related to f. For any g satisfying, g prime of x equals f. So the relationship is really, it's an undoing. The key shortcut to integrating is reversing the process of differentiating. So in English, that's the way you need to think about it. In order to integrate, you need to reverse the process of differentiation. Does anybody have a question about this? Well, this is also promising because we know how to differentiate, and lots of our derivative rules are simple. So now we're saying if we want to integrate, it looks like a lot of these integrals can come down to us just reversing those quote unquote simple rules. So let's just immediately go back to the example we've done twice now. We've done 2 of these. So note that g of x, which is 1/2 x squared, satisfies g prime of x equals x. Thus, the integral from 0 to 1 of x dx by the fundamental theorem should be g of 1 minus g of 0, which is 1/2 minus 0, which is 1/2. That's what we got. It was a lot more difficult to get that before. We had to take some limits and recognize patterns. It was not as easy. This is pretty direct. Does anybody have a comment about this or a question? Hello, 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 hello. All right. So let's look at another one real quick. So we showed using the definition we did this the other day, and this is part of your homework to do it again, that the integral of x squared dx was 1/3. That was a hard problem to do. So since g of x, which is 1/3 x cubed, satisfies g prime of x equals x squared, the FTC says that this integral could have easily been computed this way. All right, does anybody have a question about this? So we just showed, what we did is we used the fundamental theorem of calculus to verify, or to show you that we got the same answer. And using the FTC didn't take much work at all, other than us remembering a simple formula about derivatives. And so what this means, though, is a skill that you want to have is you would like to know simple sort of functions G that satisfy this. So it's useful to develop some terminology. Hold on one second. Pause. That's not good. Give me 1 second. That is the trials and tribulations of working from home. I apologize, but crumb snatchers don't give a damn that you're sitting here waiting. Although that's unfortunate too. I feel bad. I hate this. This is the worst. All right, you guys are like, I don't want to pay full tuition for this. O'Grady's a jerk. All right, so here we go. Here's what's useful. So it's useful to define new terms, notation. So if g prime of x equals f of x, we call g an antiderivative. So anti for opposite of f. So I think it was you, Heather, that you sent an email and you were talking about how you were studying the end of chapter 4. Look, most books define this term before the integration, but I just think it's silly to do that. I think this is the more natural way of doing it. Why to tell someone what something is until you need it? So now we need it, so now we define it. And then once we define it, it's useful because of the connection to use certain symbols. So in this situation, we can also write we use the integral symbol, but we don't have bounds on it, and we write it like this. Now, this C might seem completely ridiculous, and you're like, why would you write a C? Well, think about what we know about derivatives. If you have one antiderivative, you actually have infinitely many, because you can add any number to it, any number you want, and when you differentiate a number, it's always 0. So we call this here an arbitrary constant. Again, let me repeat. If f has one antiderivative, it actually has infinitely many, and this is how we describe it. We write it like this. So does anybody have a question about that at all? One other thing that is useful to do is it's also, I keep saying shorthand is useful. It is. We also write g of x, and then we put a bar a, b here for short instead of writing this. So look, there's a lot happening, and really the decision, this is just the trials and tribulations of calculus, only it's sort of amplified because we're in a summer session, and we're also in summer, we literally give the exam right after the last class, and it's just one of the unfortunate things. We don't have a finals week in summer. So there's a lot happening, but you have to make the decision. Are you going to just practice examples and sort of mimic examples, or are you going to try to take the extra time and effort to understand what's happening? And I'm not saying there's a right or a wrong way of doing it. Look, we're very short on time. You'll notice that I extended the homework till Sunday night, but I need to grade your exams before. I'm pretty sure the grades are due Monday at noon. So that's why we're on such a short time frame. And I'm trying to give you guys the benefit of the doubt. I'm letting you take these exams at home. And by the way, if you have questions about the exam, we can definitely talk about that too. But we need to do some more examples of this so that you get familiar with sort of the notation. Before I go to the next page, does anybody have a question? By the way, some people will call this an indefinite integral. So when there's not bounds, so let's make note of that. So let me write it this way. So if there are no bounds on the integral, we call it an indefinite integral. So what you might then say is, you might say, well, are indefinite integrals the same thing as antiderivatives? And they're sort of synonymous, but there's a slight technicality, but we won't let it. So again, let me just say something real clear. Let's write this down. If I write integral x dx, we know what this is. It's 1/2 x squared plus c. You can verify it. And then over here we have so this is called a definite integral. or excuse me, indefinite, excuse me. And of course, this is definite. So hopefully you guys can, you know, that helps clarify some things. I don't know if it will or won't. Does anybody have a comment or a question? Happy days are here again. Someone's chopping off the ears. Let's see. Yeah. Gonna do that in about 5 seconds. So it's important, what you should do, and your textbook does this, I believe, in section 4.9, whatever section the antiderivative is. But what you should do is it's good practice to write all your familiar derivative formulas in terms of indefinite integrals. So it's helpful to do that. So let's do some more examples. Let's look at something like 7. Okay, so let's say we're going to integrate. Let's do it. Let's just do 7a since we're at it. So instead of me writing the square root, I'm going to write it as x to the 1/2. So what I have to do is I have to remember my derivative rules, but I need to reverse them. And this comes down to practice. That's what it comes down to. You don't want to try to memorize these things. You'll notice that I didn't write them down because I think it's a bad idea to try to memorize things. My advice for learning anything is to do it. Right? I mean, what's the best way to learn? You want to learn Spanish? Why don't you take a flight and drop yourself off in Spain or Mexico City? And if you want to learn Spanish, put the movies and television on where they speak Spanish all the time. If you want to learn math, you got to do it. Memorizing things only goes so far. So when I say do it, here's what I mean. Ask yourself, what is the antiderivative of 4x squared plus x to the 1/2? Now, there's lots of ways you can train your brain to do this, but I would advise you to think about the reversing the rules. So how would you differentiate 4x squared? Well, you'd bring the 2 down, so you'd multiply by 2, and then you would subtract 1 from the exponent. We want to reverse that process. So instead of subtracting 1, we should add 1. And then instead of multiplying, we should divide. So that suggests that this should be 4x cubed over 3, and then this should be plus x to the 3/2 divided by 3/2, evaluated from 0 to 2. Now, before you go any further, you should take the derivative of that and make sure it matches what you see. Does anybody have a question about that? Comments? Okay, so why is it divided by 3? Because think of the rule. So let's sort of it's a good question. Let me get a different color here. So what's the derivative rule for the powers? So what do we know about derivatives of a power? So what's d dx of x to the power n? It's what? You multiply by n and you subtract 1, right? So what's the reversing of that? If I wanted to reverse that, instead of multiplying, I'm going to divide, and instead of subtracting, I'm going to add. So to reverse it, we would add 1 to the exponent, then divide by the new exponent. So what's the new exponent? If I take 2 and I add 1, I get 3, so I should be dividing by 3. Similarly with the 1/2, if I add 1 to a half, I get 3/2. And so I should divide by that new exponent. And again, a good way to sort of get yourself thinking you did it correctly is look at what you have on the right-hand side and differentiate it. If you differentiate it, bring down to 3, you'd get 12x squared over 3, which simplifies the 4x squared. So if you take the derivative of this function right here, you get this. It's just something that comes down to practice. I know that's a cop-out of an answer from me, but that's really what it is. I wish there was a better answer I can tell you. Does anybody have a comment or a question? Okay, so the next thing you have to do is you have to plug in 2. So if you plug in 2 to this, you get, I guess I should go back to. And by the way, we'll do some more examples and hopefully it'll become clear. When you plug in 2, you get 4 times 8, so you get 32 over 3. Plus, instead of dividing by 3/2, I'm going to multiply by 2/3, and then this becomes 2 to the 3/2. Then, of course, this is going to be minus 0 plus 0, because when you plug 0 in, it goes away. So if you simplify this, this is 1/3 32 plus 2 to the 5/2. That's one way of writing it. Now look, perhaps, and perhaps what we should do is we should maybe, you know, start with you know, look, let's go, let me do something that might sort of ease your mind a little bit. What if we did this example now? We'll sort of step back. What if we integrated from, say, 1 to 3 of x squared? So how do I undo, what's the derivative of x squared? Well, the derivative of x squared is 2x. So what would be the opposite of that? The opposite would be add 1. So the antiderivative here is x cubed over 3 evaluated from 1 to 3. And so when you plug in 3, you get 3 cubed over 3 minus 1 cubed over 3, which becomes 27/3 minus 1/3, which is 26/3. What if I integrate from, say, 0 to pi of the sine of x dx? Well, what is the antiderivative of sine? So you got to ask yourself, what function out there's derivative is sine? And so the answer is this is negative the cosine. So how do you know that? Well, check your answer. If you differentiate negative cosine, you get positive sine. And so then this becomes minus the cosine of pi minus the cosine of 0. And if you do the arithmetic there, cosine of pi is -1 cosine of 0 is 1. So you get 1 plus 1, which is 2. So if you have a question about that, feel free to ask. Any comments, questions about this? All right, so let's look at and by the way, here are some, some useful formulas. Look, yeah, again, as I said, I hate to write things down because what students tend to do is you tend to just try to memorize things instead of try to use them. How about we integrate from, say, 1 to e of 1 over x dx? Well, what function's derivative is 1 over x? Well, that's the log of x from 1 to e. And so that's log of e minus log of 1, which is 1 minus 0, which is 1. Does anybody have a comment about this question? So that's one part of the fundamental theorem and what it can do for us. Hi, Lydia. I know. Hey.
I know how to get my Oreos makeup. I have to use this bowl. Is that okay?
Yes. All right, I have class. I'll be up in a minute, okay?
Okay.
All right.
All right, Mommy.
Mommy's on a walk with Grandma.
Okay.
All right. All right, so the FTC can also be used to differentiate an integral. So if you look at the FTC, there was two pieces to it. There was a first piece and a second piece. And what it says, and it's kind of straightforward, it's actually very easy. It says something like this. It says, okay, if I have this integral whose upper bound is a variable, then the FTC says that the derivative of this is just e to the negative x squared. So what you'll start to realize is you're going to say, oh, so I just take the t and replace it with x. And yes, it's true. That's what you're doing. Now, the only subtlety here is this is only the pattern only works like that when the lower bound is a number and the upper bound is a variable. So what if we switch that? What about if instead I said, and put the variable down here, and I put, say, 5 up here? Well, what we need to do is we need to flip the bounds. So if you remember how the definition of the integral goes with this delta x is b minus a over n, what if you switch those numbers? What would be the natural thing? Well, you would flip the sign. The only thing that would change would be the sign. So what we're telling you is there's this very nice property of the integral, and that is that the integral from a to b of f of x dx is always going to be equal to minus the integral from b to a of f of x dx. So if you flip the bounds, you have this very natural sort of thing that happens, and hence that is how we define the integral where the upper bound is lower than the lower bound. Sounds confusing. Thus, d dx of the integral x to 5 of e to the negative t dt becomes minus the derivative of the integral from 5 to x e to the negative t squared dt, which just becomes e to the minus x squared with a minus sign in front. Okay, does anybody have a question about this? So you need to know how to do these things too. I gave you a couple homework problems. Problem 8 does that. And one of the things that you can do is you can you know, one of the, I shouldn't say what you, let me explain it this way. One of the things that I found is, and this is what sort of happens, it's a theme, at least from my perspective. I've been teaching calculus now for 15, 16 years. I mean, I've been teaching math at a high level at universities since, you know, for about 16 years. And one of the things I've always found, well, when I teach this class, is students really struggle with these ideas with the fundamental theorem of calculus. Like if I go to the previous page, you guys, if you practice, you'll get these patterns down and you'll be okay. But this idea of understanding this differentiating an integral, that really, it sort of is a topic that many students struggle with. And you compound that, it's conceptually difficult with the fact that it's thrown in at the end of the semester. And that typically gives students a very a hard time, you know. So you don't want to get discouraged when you're not sure what you're doing. It's just, you have to understand that this stuff is difficult. And if you're willing to accept that it's difficult, any questions? Comments? All right, so let's move on then. We're moving. It's like our cruising. So the last thing we want to do is we want to talk about what happens in the situation that the antiderivative is not obvious. So I think the best thing to do, and we're not going to be too much longer. We are running out of, this is what the problem is we're running out of whiteboard space. We're going to have to. Okay, so what happens if we go to compute this guy? But the antiderivative is not obvious. So what we want to do is we want to talk about that. I mean, much of what you're going to learn in Calc 2 is about that exact challenge. But what we want to do is we want to talk about one of the first things you can do. But we're out of board, so what I have to do, and obviously if you have to go, you have to go. But I'm going to end this session, and then that way I get 20 new boards, and then I'm going to jump right back on. So I'm saving these boards, and then I'm going to end this. I'm gonna leave for like 3 seconds, and then I'm gonna jump back on. So I'll see you in 30 seconds. Actually, I'll see you sooner than that.